Now 3 circles labeled 1, 2, and 3 around a single point charge. The radii are A, 2A, and 3A. So tell me how the areas compare. Area of a sphere, remember what it is? What is this? What is it for a sphere? Volume, right? Volume of a sphere. What do we care about right now? Area. What's the area of the sphere? 4 pi r squared, right? How do I remember that? Units. Make sure the area has square units, right? So r squared. Volume has to have cubic units, r cubed. Okay, so how do our areas compare? 4 times. And the next one? 9 times, right? Because it goes as r squared. You double r, it's 4 times as much. You triple it, it's 9 times as much. It goes as r squared. The erasers are coming out now. Okay, we got that? Electric field. How do the electric fields compare? This is a point charge, right? What's our electric field from a point charge? KQ over r squared. So what happens when r gets twice as big? 1/4. And when r is 3 times as big? 1/9. It's okay to let the equations guide you, right? Some of these equations are important. Let them guide you as we go through it. Now we're comparing flux. How does the flux through 2 compare to the flux through 1? How do we find flux? And in this case, what's it going to be? It's going to be E times A, right? Because theta is going to be 0 degrees. Because the area vector points radially outward, and our electric field points radially outward, so cosine of theta is 1. So it's just the electric field times the surface area. We okay with that? That's where the negative sign comes in for the flux. So maybe I should point that out now. Our area vector always points out from the surface we're defining. So this is a sphere, so our area vector points out, and our electric field is pointing out, so that means there's 0 degrees between them. So cosine of 0 is 1. We just get the electric field times the area. If the electric field pointed in, if that was a negative charge, I'll just draw it over here. Negative charge has electric field lines pointing in like that. And I draw a sphere around it, and I want to know the flux through that sphere. My area vector points outward. That's the definition. It always points out from the volume that's enclosed by my shape. In this case, it's a sphere. And my electric field points in, so I've got a cosine of 180 degrees there. So in this case, my flux is going to be less than 0 because there's that cosine 180 that comes into play. Okay? We had to pick one direction to be positive. We said out's positive. All right, so what do we get? The flux through surface 2. How does that compare to the flux through surface 1? It's, what is it? It's electric field times the area. So the area of surface 2 is 4 times bigger than the area of surface 1. But we have to multiply it by the electric field on that surface. And what happens to the electric field as we move further away? It goes down by a 1/4 factor, right? So what do we get when we multiply those together? The same thing. The flux doesn't change. You see that now? If you just look at the field lines here, the same number of field lines, 1, 2, 3, 4, 5, 6, penetrate the first surface, the second surface, the third surface. The only way we can get more field lines to penetrate the surface is to add another charge in there to create more field lines. You could almost think of it as a faucet. The plus sign, a plus charge, is a faucet with water coming out of it. A minus charge, a negative charge, is a drain. Water can go into that, right? So do you have more plus charges? Do you have more faucets inside your surface? Then you're going to have water flowing out. If you have more drains, you're going to have water going in. So think about it in those terms. But if the faucet's running here, the same amount of water that's going through the first surface is going to come through the second surface, is going to go through the third surface. The flux is going to be the same through all of those. Okay? You buy that?
It's just kind of like a ripple effect of droplets down in water, and then once the waves get hotter and hotter, the ripple goes slow. Yeah, you hear it goes farther, and it goes farther, it's slower.
It's a little different, but I understand you're trying to make the analogy to if you drop a stone in water, the ripples start to move away, and as they move away, the speed maybe changes or something is different about it. I think it's a slightly different effect, but the idea here is that the number of lines, they're spreading out, right? So they're getting weaker. The electric field gets weaker and weaker as you move away, but the surface area of our sphere gets bigger and bigger, and the combination, which tells us sort of how many lines are penetrating the surface, stays the same, is constant. The only way that can change is if all of a sudden we have more or less charge inside of our surface. Okay? So what's our moral? The total electric flux into or out of an enclosed surface is proportional to the charge inside the surface and does not depend on the what? The shape of the surface, the area of the surface, the area, shape. What's that? Okay, it's proportional to the charge inside, and it does not depend on the area or shape of the surface. In this case, we're using circles, spheres around point charges because that makes it very easy for us to calculate the flux. But it turns out these could be arbitrary shapes. We could have put a peanut shape around it. It just would have been an ugly integral to solve, but it would have given us the same answer if we could have solved it. Okay? Okay, flip it over. Two spheres labeled 1 and 2, equal radii. We're trying to compare the flux through surface 1 to the flux through surface 2. I don't know if either one of them is 0. Any of them 0? Which one is the flux greater? You could literally count the lines penetrating the surface. In case 1, every single line is going out of the surface. They are all producing positive flux. How about circle 2, sphere 2? Some of them are going in and some are going out. If you look at how they intersect the surface. Let's see, right here. You've got one coming in. Here you've got it coming out. Coming in, going out. Going in, going out. So some of those that are going in are producing negative flux. The ones coming out are producing positive flux. There aren't as many lines as with the other circle. The other circle has more lines. Every line is producing positive flux. So what's the verdict? One has to be more, right? We good with that? Every line going through surface 1 is producing positive flux, and there are more of them. So 1 has to be greater. How about the second part? Can 1 be negative? Can 1 be 0? No, because we know there's flux and we know it's all positive, right? It can't cancel it out. It's all positive. So 1 can't be 0. Can 2 be 0? 2 could be 0. I'll cut to the chase. 2 is 0. All right? 2 is 0. Each one that comes in and creates some negative flux goes out the other side. Each ray that comes in goes out the other side and produces some positive, and they all cancel out. We end up with 0 flux. How else do we know it was 0? Go back to page 2. What was the moral on page 2? Did we get it? Actually, it was the moral on page 1, which we then repeated on page 2. The total electric flux into or out of an enclosed surface is proportional to what? The charge inside. Is there any charge inside surface 2? None. So the flux has to be 0. If I drew sort of a three-dimensional shape that looked like this instead of a sphere, what you're going to get is the electric field. The flux on this surface is the electric field times the area, because I've now drawn it with a constant radius. So the electric field is constant everywhere over that surface, right? Now it's a lot stronger over this surface than it is over this one, isn't it?